Here is a cube built from matchsticks. Let's count its parts, one kind at a time. The corners, where the sticks meet, 8. The edges, which are the sticks themselves, 12. The faces, the flat panels, 6. Now try one strange sum. Take the corners, subtract the edges, then add the faces. 8 minus 12 plus 6. That comes to 2. It's an odd little sum, isn't it? Why subtract the edges at all? And why should the answer land on 2? Most likely it's just a quirk of cubes, a coincidence with these particular numbers. Then again, maybe it isn't. There's one easy way to find out. Let's test that same sum on shapes that look nothing like a cube. If it keeps landing on 2, we've found something real, not a fluke. By the end, you'll have a law you can genuinely trust and even use to predict a count you never actually made. So let's start counting, shape by shape. Start with a triangular pyramid, 4 triangles leaning together into a single point. Count the same 3 things. Corners, 4, edges, 6, faces, 4, since the floor is a triangle too. Now the same strange sum, 4 minus 6 plus 4. Let's work it through. 4 minus 6 is negative 2. Add 4, and you're right back at 2. A shape with no square anywhere, and it still lands on exactly 2. The numbers were completely different from the cube, and yet the answer came out the same. One match is a coincidence. 2 starts to look like a rule. Try a square pyramid next, like a tent with a square floor and a point on top. 1 square base, 4 triangles climbing to the tip. Count corners, 5, edges, 8, faces, 5. Then run the sum again, 5 minus 8 plus 5. 5 minus 8 is negative 3. Add 5, and again the answer is 2. Different corners, different edges, a completely different shape, and yet the sum doesn't seem to care at all. That's 3 solids now, and every single one of them keeps settling on the very same number, 2. Here's a triangular prism, shaped like a bar of chocolate with triangle ends. Corners, 6. Edges, 9. Faces, 5. 2 triangles on the ends and 3 rectangles around the sides. 6 minus 9 is negative 3. Add 5, and there it is yet again, 2. Let's gather these in a table, the way you might in a notebook. Cube, 8, 12, 6. Triangular pyramid, 4, 6, 4. Square pyramid, 5, 8, 5. Triangular prism, 6, 9, 5. 4 solids, and not one of them looks like another. Now read the last column. Corners minus edges plus faces. The cube gives 2. The pyramid gives 2. The square pyramid gives 2. The prism gives 2. 4 different shapes, 4 different sets of numbers, and every single row lands on exactly 2. Let's push the numbers much higher and see if that finally breaks it. A pentagonal prism, 2 5-sided ends joined all around by upright rectangles. It has many more parts than the little tetrahedron did. Count slowly. Corners, 10. Edges, 15. Faces, 7. 2 pentagons and 5 rectangles between them. Bigger numbers this time, but the sum works out exactly the same. 10 minus 15 is negative 5. Add the 7 faces, and you land right back on 2. The shape got larger and busier, every count grew, and yet the answer still didn't move by a single inch. Now a solid that should tip the balance over. An octahedron, 2 square pyramids glued base to base, like a diamond. For the first time it has more faces than corners. Corners, 6. Edges, 12. Faces, 8. With more faces than corners, you might expect the sum to overshoot 2 this time. Let's see. 6 minus 12 is negative 6, add 8. And it settles on 2, exactly 2, one more time. Even with the balance tipped the other way, the answer holds completely firm. So why is it 2 every single time? Here's the reason. Take the cube and squash it completely flat, like pressing its shadow down onto the floor. You get this flat map of dots and lines. It still has the same 8 corners and the same 12 edges, with nothing at all lost in the flattening. This flat map cuts the page into little closed regions. Count them carefully, there are 5. And a flat drawing like this obeys its own rule. 1 you can check right here. Corners minus edges plus regions equals 1. Test it. 8 minus 12 plus 5 really does come out as 1. But flattening quietly hid one face, the one we pushed the whole shape through. It became the entire outside of the map. Add that outside face back in, 5 regions turn into 6 faces, and 8 minus 12 plus 6 is 2. That one hidden outside face is why a solid gives 2, not 1. If a cube feels too easy, try the hardest everyday solid you can find. A football stitched together from flat leather panels, 12 pentagons and 20 hexagons, which is 32 panels in total. With that many separate pieces sewn together, surely a sum this simple finally cracks. Count it fully, and you find 60 corners and 90 edges. 60 minus 90 is negative 30. Now add the 32 faces, and you come straight back to 2. Hundreds of stitches and seams across the whole ball, and it gives the same quiet answer we got from a single little cube. Is it honestly every solid? Almost. There's one way to break it, and that's a hole. A solid shaped like a picture frame, with a hole passing straight through the middle, gives 0 instead of 2. So the rule is for solids without a hole. Every one of those lands on 2. Step back and look at the whole collection we've built. A cube, a pyramid, a prism, an octahedron, a football, all wildly different from one another. Yet through every single one of them, one number stayed pinned firmly in place. Corners minus edges plus faces, always coming out 2. A number that refuses to change, no matter how you reshape the thing, has a name. It's called an invariant. This particular invariant is a famous one. It's known as Euler's formula. Descartes noticed it first, and Euler proved it for good back in 1732, almost 300 years ago. Your turn now. Here's a pentagonal pyramid, a 5-sided floor rising up to a single point. Count its corners, its edges and its faces, then do the sum yourself before I do. Pause the video here and take your time. Let's check it together. The floor has 5 corners, plus the single one on top, so 6 in all. Edges, 5 around the base and 5 running up to the point, 10 altogether. Faces, 5 triangles and the base itself, 6. 6 minus 10 plus 6 is 2, exactly as you'd expect by now. Now use the law instead of counting everything by hand. A hexagonal prism has 12 corners and 18 edges. How many faces does it have without imagining a single one of them? Pause and let the formula do the work for you. Corners minus edges plus faces must be 2. 12 minus 18 is negative 6. So the faces have to carry you from negative 6 all the way back to 2, and that takes 8. 8 faces, 2 hexagons and 6 rectangles. The formula counted them for you. One last one, turned inside out. An octahedron has 8 faces and 12 edges. How many corners must it have? Pause here. This time you already know 2 of the counts, and you're solving for the third. Corners minus 12 plus 8 has to be 2. That's corners minus 4 equals 2. So the corners must be 6. And 6 is exactly what we counted on the octahedron earlier. Know any 2 of the 3, and the formula fixes the last one. This isn't just a game with matchsticks. Engineers rely on it when they design geodesic domes, where the panels and struts all have to add up correctly. It sits quietly underneath the mathematics of networks and maps, and graphic software uses it to check that a digital model is properly closed and fully sealed. So take any solid without a hole, count its corners, its edges and its faces, then do that strange little sum. The answer is always 2. Count carefully enough, and you can uncover a real law all by yourself, then turn it around and trust it to tell you what you never actually counted. That's all for this video.